Okay, so today we're going to work on everybody's favorite word problems. We're going to be using the calculus to solve applied maximum and minimum problems. We'll begin here. It says, how should two non-negative numbers be chosen so that their sum is 1 and the sum of their squares is as large as possible? So we're looking for two non-negative numbers so that their sum is 1 and the sum of their squares is as large as possible. Okay, so first number, we should label things. Our first number will be x. Our second number will be y. And so then so that their sum is 1 and the sum of their squares is as large as possible. So what we want to do is we want to maximize sum of the squares. And so then we need a formula for the sum of the squares. And so then we'll call the output S for sum of the squares. And the sum of the squares is given to me by this formula, x squared plus y squared. But we want a function of only one variable. And so then we have to be given a constraint that relates the two variables. And so the constraint is that so that their sum is 1. So then that gives me, if their sum is 1, then these can't just be any two numbers. X plus y has to equal 1. Then we can take this constraint and solve for y. So y is x minus 1. And what that allows me to do is that allows me to take the formula that I'm trying to find the absolute max of and replace my y with x minus 1. So now I get the formula x squared plus x minus 1 squared. And what you should do is you should think about, well, what x's am I allowed to use? It says, how should two non-negative numbers, so that means that for x, my smallest possible value is 0, because that's non-negative, be chosen so that their sum is 1. And if they're non-negative numbers, then the biggest that x can be is 1, because once I have a number bigger than 1, then no way for me to add it with another non-negative number and get 1. So the reason why this is important is because now we have a continuous function on a closed interval, and we're guaranteed to have an absolute max and an absolute min. We're guaranteed to have a sum, a biggest sum that's possible, and a smallest sum that's possible. Okay, so we went over how to do this last time then. So first we should clean this up. This is x squared plus 2x squared, plus x squared minus 2x plus 1. And we can clean this up again, and this becomes 2x squared minus 2x plus 1. So we're just trying to find the absolute max on the interval from 0 to 1 of this function. Well, we did that last time. We saw that that is going to happen where at the critical numbers, where 4x minus 2 equals 0, or at the endpoints, right? And so the critical numbers and the endpoints are what we're going to see. You can see that the only thing that makes that derivative 0 is 1/2, and the endpoints happen at 0 and 1. And so then we plug in 0 into my sum, because that's what I'm trying to maximize. And so when I plug in 0 in for x right here, so that we can just use x and not have to find y, then I will get 1. When I plug in 1, I could plug it in right here, then that term goes away and we end up 1. You could plug it in here as well. 2 minus 2 is 0, plus 1 is 1. but I saw that using this formula here would make this term go away. And finally, when you plug in a half, and then your sum is a quarter plus, times 2 plus, minus 2 times a half. You're plugging in a half plus 1. And so 2 times a half is 1, so minus 1 and plus 1, those go away. And so then you get a half. And so at a half, you get a half. And so it says, don't forget to answer the question. Find how should 2 non-negative numbers be chosen. So one number is, if we want, is 1, and the other is 1 minus 1 is 0. Or you could use 0 here and 1 here. Either way, so 1 and 0. Okay. So the boundary of a field is a right triangle with a straight stream across its hypotenuse and with fences along its other 2 sides. Find the dimensions of the field with the maximum area that can be enclosed using 1,000 feet of fence. So what I expect you to be able to do is I expect you to be able to draw your own pictures. I'm not going to provide you with a picture. So here you have a stream, and you're going to enclose some cows, so that to minimize the fencing, you'll use the stream or the river as part of your boundary. So we'll put in our fence right here. And we're going to come up here and then go off this way. Okay. So the boundary of a field is a right triangle. So that's a right angle. With a straight stream along its hypotenuse and with fences along its other 2 sides. Right? So find the dimensions of the field. The problem did not tell us that these had to be the same, so we'll put x and y. With the maximum area. So we want to maximize the area. So we need a formula for the area. What we have is a triangle, and the formula for the area of a triangle is 1/2 the base times the height. Again, to do our calculus on this and find the critical points and the absolute max and the absolute min, we can't have 2 variables. We can't have the x and the y. So we need to get rid of one of these variables. So we need a constraint. And so then your constraint comes from the fact that we don't have an endless amount of fencing. It says find the dimensions of the field with the maximum area that can be enclosed using 1,000 feet of fencing. So then you only have 1,000 feet of fencing. You're going to use some of the fencing here and some of the fencing here. And so then your constraint is that x plus y has to equal 1,000. So again, you can take your constraint and solve for y. So y is equal to 1,000 minus x. And so then you can create your area just as a function of one variable. So your area is 1/2 the base times the height, 1,000 minus x. And again, you should get in the habit of writing down over what interval, what values of x are you allowed to use. And it should make sense that if you wanted to, your x could be 0. You could put the fence right along the river with with nothing there. Of course, that would be impractical, but still, right? So we have so that so that the calculus works, we can include the 0, and then we could use all the fence along that side, and we have 1,000 feet of fence, so we would do that. Notice that with either 0 or 1,000, the area is 0. Also notice that because we're looking at a continuous function on a closed interval, we're guaranteed to have an absolute max and an absolute min. So by including 0 and 100, we guarantee that our calculus will work out. We also know that it can't happen at the endpoints, because at the endpoints our area is 0. So now we can work on figuring out where are the critical points. So again, make this a little easier so that we don't have to use the product rule. We can distribute, and we will get 500 x minus 1/2 x squared. We need the critical numbers. And again, what I encourage you to do is from time to time pause the video and see if you can't do that next step yourself, right? And then you can compare it. So this way you know if you're getting the hang of this or not. But once we have the formula, the calculus is actually now pretty easy. We know that the absolute max has to happen at the endpoints or at the critical points, and it can't happen at the endpoint. So now we just got to find the critical points. And the critical points for this is pretty simple, because the derivative is 500 minus x, and so then it looks like the only critical point is at 500. So then we're looking for the absolute max, and so we know that it has to happen at the endpoints or at the critical points. And at the endpoints at 0, we're going to get an area of 0, and at 1,000 we're going to get an area of 0. So the so that 500 has to be the value that I use to get my maximum value. So we can just plug that into the area formula. Area of 500 is equal to 500 times 500 minus 1/2 times 500 squared. Okay, so plugging that into the calculator, I get 125,000. And this is square feet, right? Everything was in feet. And now make sure that you answer the question. Find the dimensions, right? So the dimensions are 500 by 500. Put them on the picture. And let's move on. A rectangle is to be inscribed in a right triangle having sides of length 6 inches and 8 inches and 10 inches, right? Find the dimensions of the rectangle with the greatest area. Assume that the rectangle is positioned as in figure exercise 6. Right? So here's the picture, and just to give you an idea of what's going on. We can start here at this corner, go over as far as we want, right? Go up to the hypotenuse and come back across, and we would get a different size rectangle. So you can do that. Just go over a little bit, come up here, come over here, and you would get a different size rectangle, right? And so we want to figure out what are the dimensions? How big can I make this rectangle? Right? Okay, so let's go ahead and label some things, right? We can just label this part right here, x, and this part right here, y. Find the dimensions of the rectangle with the greatest area. We want to maximize the area. We need a formula for that. So with what I have on that picture, you should write down what the formula is. The area is equal to x times y. Again, what's wrong with this is that it has too many variables, and so you need a constraint. Now in this problem, you weren't given the constraint verbally. You have this picture, and so somehow then you need to relate what x and y are, right? But if you notice right here, you have this little triangle here. Right here, that is similar to the big triangle, right? Now, if the whole side here is 8 and down here is y, then take a moment, pause it, figure out, I took it out, it's over here. What expression gives me the length of this side right here? And so that expression should be 8, the whole thing. Take away what you don't want, y, right? Now, this right here is the same as this right here, and so that one is x. And so similar triangles pop up a lot in this section, so make sure that you can handle that. And so then this rectangle right here is similar to the whole rectangle. So the ratio of this vertical side to this horizontal side, 8 minus y over x, should be the same thing as for the whole rectangle. The vertical side over here is 8, and the horizontal side over here is 6. Okay, and so this is the equation that relates x and y. So what we can do is we can clean up this equation by cross multiplying. 48 minus 6y equals 8x. And then we can go ahead and solve for x, since that's what's going to be easiest. So we can divide both sides by 8, and we get our constraint. And our constraint is that x has to equal 48 minus 6y divided by 8. To make that easier, the 48 divided by 8 is 6, and 6 divided by 8 reduces down to 3/4. 6 minus 3/4 y. And so now we can go and we can substitute in the 6 minus 3/4 y in for x. So then you get 6 minus 3/4 times y times y, which will then be 6y minus 3/4 y squared. Okay? And again, you should figure out over what interval, what values of y am I allowed. So y was the length of this side over here. Y was the length of this side over here. And so you could see that you could use a y value of 0, or you could use a y value of 8. But again, when you use 0 or 8, the area of the rectangle that you make will be 0. So, but that's okay, because now you know what it is at the endpoints, and so then you can tell that your absolute max and your absolute min won't happen at the endpoints. They have to happen at some point inside the interval. Okay, so now that we're there, we have a continuous function. This continuous function right here on this closed interval, we're guaranteed an absolute max and an absolute min, and it's got to happen at the endpoints or the critical points. So let's go find the critical points. To find the critical points, those are just the zeros of the derivative. So 6 minus 3/2 y. Now when you bring down the exponent, the 2 times the 3/4 will give you 3/2. If you don't want to do that in your head, you can put in 0 for your a prime, and then you get 6 minus 3 halves y. So then 3 halves y will equal 6. Multiply both sides by 2/3. And so then y is equal to, 3 goes into 6 2 times, and 2 is 4. So y is 4. So find the dimensions. We need the dimensions. But we still have to figure out, which one's my absolute max. Of course, when I put in 0 or 8, sorry, not x, y, a of y, I'm going to get an area of 0. So probably I have to get a bigger area than 0 at 4. And so then you get 24 minus 4 squared is 16 times 3 is 48, divided by 4 is 12. And so you get an area of 12, right? And so then that is bigger than the zeros, so this is your absolute max. So then we already know that y is 4, but it says find the dimensions of the rectangle. And over here, it says that x is equal to 6 minus 3/4 y. So when you put the 4 in for y, the 4's will cancel. And so then x is equal to 6 minus 3/4 times 4, which is 3. Okay. So again, I encourage you to try these problems on your own, and then you can see how I did it. Now, sometimes with these problems, these are challenging for people. So if you just want to watch these, that's fine too. A rectangle has its lower corners on the x-axis and its 2 upper corners on the curve y equals 16 minus x squared. For all such rectangles, what are the dimensions of the one with the largest area? All right, so again, expect you to be able to draw a picture. A rectangle has its lower 2 corners on the x-axis and its upper 2 corners on the curve y equals 16 minus x squared. You should recognize that 16 minus x squared is just taking the negative x squared parabola and moving it up 16 units. So you're moving it up here. You should recognize by inspection that it's going to cross the x-axis at negative 4 and 4. 4 squared is 16. 16 minus 16 is 0. Negative 4 squared is 16, and you get 0 as well. What you are doing is you're making a rectangle by picking some point on the x-axis here, we'll call it x, going up to the curve, right? And we'll call that y. So this is the point xy. Cutting across and then coming back down. But because this is a parabola and it's nice and symmetric, you should know what the coordinates of this point are. Right? So the y coordinate didn't change because you came straight across. Y. But you're on the opposite side. So that should be negative x. Right? So we're trying to maximize the area. With what I have on the picture here, you should write a formula for the area, and because I have x's and y's, it should be in terms of x and y. It's a rectangle, so you pause the computer, see if you can't figure out a formula in terms of x and y for the area, right? Now, it is a rectangle, so we need to figure out what is the distance all the way across here. And since you're going x and then x in the other direction, because that's at negative x, your length there is going to be 2x, right? The distance from here to here is just y. So area is equal to 2xy. Again, what's the matter with this? too many variables, right? We have too many variables. But this isn't just some random point out in the xy plane. This point is on the curve. Y is equal to 16 minus x squared. So your constraint is given to you by the fact that in this problem, your y is equal to 16 minus x squared. Okay. So then we can substitute and we can write our area as a function of x, 2x times 16 minus x squared. And you should also ask yourself, well, over what interval? Remember, we first started at 0. It doesn't make any sense to start over here. We should start at 0. We should start here at 0 and move over to the right. So the x value here represents how much I moved over to the right, right? And so how much I move over to the right, I could move over as little as 0 or as much as I cross the x-axis over here, as much as 4. So that is my domain. So again, I'm looking at a continuous function on just this closed interval, so I'm guaranteed to have an absolute max and a min. It's either going to happen at the endpoints, but of course if I go over 4, then to get on the curve, I'm already on the curve, I will go up 0 and my area will be 0. If I go over 0, and then it'll be a rectangle that has no width, and that area will also be 0. So at the endpoints, I'm just going to get 0, and so then we don't have to really test those, right? But we need the critical points, so we expand this, distribute 32x minus 2x cubed. Find the derivative. A prime of x will be 32 minus 6x squared. And the critical number is 32. Sorry, so 32 minus 6x squared equals 0. So then 32 will equal 6x squared. So then you divide both sides by 6 and you will get 16 over 3 is equal to x squared. And then if you square root both sides, you get 4 over the square root of 3 is x. Again, because at the endpoints you get 0, this has to be your absolute max. Your absolute min is 0 that you get at the endpoints, right? So we're just going to go ahead and leave that alone. I'm not going to make the table. Next, we want to make sure we answer the question, what are the dimensions of the one with the largest area? So we just figured out the x value, right? We didn't figure out the dimension, right? So again, all we figured out, make sure that you answer the question. All you figured out is how far you go to the right. And the answer is 4 over the square root of 3. But we want to know how long is it along here. And so then what that is twice the x, right? So then we'll call that the length. A rectangle has a length and a width. 8 over the square root of 3. And then the width is the y value, and the y value is 16 minus your x squared. So minus 16 over 3, which is 32 over 3. Okay, so we have the dimensions, we have the length and the width. It's time to move on. A wire of length 12 can be bent into a circle, bent into a square, or cut into two pieces to make both the circle and a square. How much wire should be how much wire should be used for the circle if the total area enclosed by the figure is to be a maximum? Okay, so how much wire is to be used for the circle? So we'll say x is equal to the amount of wire for the circle. It helps if you label things. It's very difficult to just read this problem and just start figuring out everything. And so then we're going to take a wire and bend it into a circle and a square. And so then we'll let y equal the amount of wire to be used for the square. Okay, so if the total area enclosed by the figure is to be a maximum, so we want to maximize the area. And so we need a formula for the area. Now, if you think about it, if x is the amount of wire for the circle, then so the area of the circle is going, the area of the of both is going to be the area of the circle, which is given to us by the formula pi r squared, plus the area of the square, which is the area of a square is s squared, whatever the length of one side is. Notice that I have two things here, x and y, and now I've just brought in these other variables, r and s, but hopefully that's going to be clear why in just a little bit, right? The amount of wire I use for the circle is not the radius of the circle, right? The amount of wire I use for the circle is the circumference of the circle. So then the circumference of the circle I make will be 2 pi r, and it will be x. So that I can then solve for r in terms of x, and so r will be x over 2 pi. Likewise, for the square, 4 times s gives me the perimeter of the square, how much wire I have on the square, but that's what I'm using, that's a y, right? And so then I get that s is equal to y over 4. So now I have that my area will equal pi times my radius squared, x squared over 4 pi squared, plus s squared, which is y squared over 16. Notice that one of those pi's will cancel out, and this cleans up to x squared over 4 pi plus y squared over 16. Now this is nice, but we still have too many variables, right? So, but if x was the amount of wire for the circle and y was the amount of wire to be used for the square, well, and we had a total of 12 inches, then the constraint is that x plus y has to equal 12. And since we are only interested in how much wire should be used for the circle, we don't really need how much wire will be used for the square, so we'll solve for y, 12. minus x. So then area is equal to pi x squared. Oh, I'm sorry, not pi, we cleaned it up already. X squared over 4 pi plus y squared, 12 minus x squared over 16. Okay. And so then this will be x squared over 4 pi. Well, we're just going to go ahead and leave it like that. Just go ahead and we're not going to do the algebra to clean that up. Okay. But we are going to figure out, what are my dimensions. So my dimensions, my interval, x is the amount of wire for the circle. I could use all the wire on the circle, or I could use none of the wire on the circle. So I could use 0, or I could use 12. Now, if you notice, if you put in 0 for x, you don't get 0 for your area. And if you put in 12 for x, you don't get 0 for your area. You're going to have to check the endpoints, right? So you have a continuous function on a closed interval. Your interval's from 0 to 12, but you no longer have the endpoints giving you 0 like we did in a lot of our problems. Okay. So next we have to find the critical points. And so then to find the critical points, I need to find the derivative. And so just because you see over 4 pi doesn't mean you use the quotient rule. This is just a constant. So we can just bring down the 2, which will cancel out this 4, and give us x over 2 pi. Plus, for this one, this is a composition. So you bring down the exponent and you will get 12 minus x to the 1. But the 2 that you brought down will make this 16 and 8. Times the derivative of the inside. But the derivative of the inside is negative 1. If you multiply both sides by 8 pi, so now we want to figure out what makes this 0. And so then 0 is equal to x over 2 pi minus 12 minus x over 8. This is just a linear function, but to make my life a little easier, I'm going to multiply both sides by 8 pi. All right, so let me go ahead and make some space here. Okay, so we're trying to figure out what's going to make this expression here 0. And so we're going to multiply both sides of this equation by 8 pi. So on the left, we will still get 0. On the right, on this first term, the pi's will go away, and I will get 4x. And on the second one, the 8's will go away, and I'll have to distribute the minus pi. So I will get minus 12 pi minus pi times x. Add the 12 pi to both sides. What's left on the right side is the 4x minus pi. Factor out the x. Sorry, the 4x minus pi x. And so you get 4 minus pi times x. Divide both sides by 4 minus pi. And so x is equal to 12 divided by 4 minus pi. 12 pi divided by 4 minus pi. You should always ask yourself, does your answer make sense? And so this didn't make sense. When I plugged it into the calculator, I was getting x was 43. That was outside of my interval. And I was looking to see where I made a mistake, and I made the very common mistake that people make all the time. This minus needs to get distributed to both. So this should be a minus 12 pi, but then this should be a plus, because this minus here changes to a plus. Okay, so then that should be a plus. Something is going on with my pen. Hey, so I figured out the pen issue. So that should now be a plus. And so then we get a value of about 5.3. So x is approximately 5.3. And so then that does fit my interval. We're only looking for x's between 0 and 12. And so we're good. Okay, so next we need to figure out, we figured out our one critical point. So x is approximately 5.3. But it says how much wire should be used for the circle if the total area enclosed by the figure is to be a maximum. And so then again, what I expect you to do is I expect you to make a table. Right? And so let me make some space here. The screen is only so big. Okay, so then you're going to you're trying to maximize and minimize the area. You're looking at this function here over this interval, so you're guaranteed to both have an absolute max and an absolute min. X area of x. And so then we're putting in 0, we're putting in 12, and then we're putting in this 12 pi divided by 4 plus pi. And again, the quickest way to do this is to put this formula into your calculator and then use the table feature. Okay, so once you put that into your formula, at 0 you get 9. Now, if you didn't, x was how much you used for the circle. If you didn't use any for the circle, and you would use it all on the square, and 12 divided by 4 is 3, and the area of the square would be 9. If you're not getting 9, you put it into the calculator wrong. If you use all of the wire on the circle, you will get an area of 11.459. And if you use the critical number 12 pi over 4 plus pi, then you will get an area of 5.0409. Okay, and so then you can see that this is your, that this is your that this is your, not this, this is your absolute max. And this is your absolute min. So one of them was at the endpoints, the other one was at the critical point. So how much wire should be used for the circle if the total area enclosed by the figures is to be a maximum? 12 inches should be used. And how much for it to be a minimum? The 12 pi over 4 plus pi. A rectangular page is to contain 42 square inches of printable area. The margins at the top and bottom of the page are each 1 inch. One side margin is 1 inch and the other side margin is 2 inches. What should the dimensions of the page be so that the least amount of paper is used? Okay, so we're going to have a rectangular piece of paper. This thing is not cooperating. There we go. We're going to put margins on it. So we're going to have the top and bottom are 1 inch. And the sides are 1 inch and 2 inches. Right, so the top and bottom. So what should the dimensions of the page be so that the least amount of paper is used? Okay, so since we have issues with subtractions, and subtractions causes more problems, we're going to let this be x and let this be y. Right? And so then if that's the case, then the dimensions of the paper, which is what we're trying to minimize, what should the dimensions of the page be so that the least amount of paper is used? So those instructions there are asking us to minimize the area. But the area is the length times the width of the paper, right? And so then we're going to go ahead and write an expression for the length. Now pay attention to the fact that on the left here you have 2 inches and over here you have 1 inch, so you should write an expression. Take a moment to write down an expression for how long this is. And it works out to be x plus 3. 2 inches from this side, 1 inch from that side, so it's this x plus 3 more inches. The dimensions up vertically are from here to here is y, but you have 1 inch on the bottom and 1 inch on top, so that's just y plus 2. And so then the area is what you're trying to maximize, and so then the area is x plus 3 times y plus 2. Now again, too many variables, and so then we have a constraint though, that we are to have a total we are to have a total printable area of 42 square inches. And so that's kind of why I used x and y here, because I saw that. I knew I was going to relate x and y, so I was going to relate these right here with that information, so that's why I chose x here and y here. So the constraint is that x times y has to equal 42. So now y is equal to 42 divided by x. So then we can then write our area as x plus 3 times y is 42 divided by x plus 2. Okay, but again we should what values of x are allowed, right? So x is the distance from here to here, and if we're going to have at least an inch on the right and an inch on the left, then oh, I'm sorry. So x is just the distance from here to here, and we can use x has to be bigger than 0. It can't be equal to 0 because then we can't satisfy our constraint, and there's no maximum, and so then we don't have a continuous function on a closed interval, and so we have to be a little bit more careful here. Let's expand this out. Okay, so just take a moment to expand this out. You know, take your time, pause it, do some of the work, hit play, see how you did it, see how I did it. You know, see if we can get through this that way. So the x times the 42 over x will just be 42. The x times the 2 will be 2x. And the 3 times the 42 over x will be 126 over x. Will be 126 over x, okay? And then the 3 times the 2 is 6. We're not guaranteed to have an absolute max and an absolute min because we're not on a continuous function, but we can look at the critical points. And so then our first derivative, the 42 goes away, right? The derivative of the 2x is just 2. And the derivative of 126 over x will be minus 126 x squared. I'm sorry, not x squared, x to the negative 2. Right, so this is x to the negative 1. Bring down the exponent, that makes it a minus. Take 1 away from the exponent, x to the minus 2. Plus the 6, that goes away. Right. So to find the critical numbers, we figure out what makes this 0. And so then we have 0 is equal to 2 minus 126 over x squared. So if we add the 126 over x squared to both sides, we get 126 over x squared is equal to 2. And so then 126 is equal to, clear the fractions by multiplying both sides by x squared, 2x squared. Divide both sides by 2, and you get x squared is equal to 63. And so then x is equal to the square root of 63. The negative square root of 63 doesn't make any sense in the context of this problem. And so x is equal to the square root of 63 is my only critical number. But what do I do with that, right? I mean, I can't just assume that that is the answer. So please make sure that you don't assume that that's the answer. You can't plug in the endpoints because you don't have endpoints. So then what we do is we find the second derivative. And so then the second derivative, there's only one critical number. And so what we learned in the last section is if there's only one critical number, if it's a relative max, it's an absolute max. If it's a relative min, it's an absolute min. So we look at the second derivative, which would then be positive 252 over x cubed. You can see then that when I put in the square root of 63, there's no chance for this to be negative, that will be positive. Therefore, it's concave up. Therefore, it's a relative min by the second derivative test, and since there's only one, therefore it's a relative max. I'm sorry, therefore it's an absolute max. So then our answer is x is equal to the square root of 63. But that's not what we were being asked. It says, what should the dimensions of the page be, right? So x is just how long it is along the printable space. So I shouldn't have circled this yet, right? So the dimensions are going to be the square root of 63 plus 2 by, and then for the y, remember the y was 42 divided by x, so then that's going to be 42 divided by the square root of 63. But again, we want the dimensions of the paper, which go all the way up here, which you have to add 2. And there we go. Those are my dimensions. So that is my answer. Let us move on. A closed rectangular container with a square base is to have a volume of 2,250 cubic inches. The material for the top and bottom of the container will cost $2 per square inch, and the material for the sides of the container will cost $3 per square inch. Find the dimensions of the container of least cost. So a closed rectangular container, so you have a box, it's a rectangular box. There's your rectangular box. It's with a square base. So since it's a square base, this is x. And this is x. So this is x, and then the height is different, so that's why. It's not drawn to scale, I apologize for that. Okay, so again, we want to find the dimensions of the container of least cost. So we want to minimize the cost, right? And so the cost, you're being told that the material for the top and bottom of the container will cost $2 per square inch, right? So then for the cost, you need the area because it's $2 per square inch. So the area of the base is x squared, but you have 2 of them, so you need to multiply by 2, and then because you have a top and a bottom, and it has a top and a bottom, and then you have to that's the area, and then you have to multiply by the cost per square inch, which is another 2. Plus, now for the sides, you have sides that xy here, xy here, and then xy here, and so you have 4 sides that each measure xy. And so then for the sides, that material costs $3 per square inch. And so if we clean this up, you get 4x squared plus 12xy. Okay. But again, too many variables, so we need to look for a constraint. A closed rectangular container with a square base is to have a volume of 2250 cubic inches. So the volume is the length times width times height, which is x squared times y. And so then since your volume is going to be 2250 cubic inches, so 2250 will have to equal x squared y. And so then y will have to equal 2250 divided by x squared. So we can put that in for y, and we can see then that our cost is 4x squared plus 12 times x times 2250 over x squared. The 12 times the 2250 is 27,000. divided by x. Or you can write it as, to make it easier to differentiate, the x over the x squared, you're going to get 1 over x. So you're going to get x to the negative 1. And again, what interval? The only thing you can do is say that x has to be positive, right? There is no upper bound on it, and there is no lower bound on it. You can make x as small as you want, but that'll make y bigger and bigger. So again, we're not guaranteed to have an absolute maximum and an absolute minimum because we are looking at a continuous function. I'm sorry, because our function is not on a closed interval. But we can go and look for the critical points and see what those tell us. When we get 8x minus 27,000 over x squared. X cannot be 0, so to find our critical points, we can set our derivative equal to 0 and clear the fractions. And when I do that, if I multiply both sides by x squared, I will get 8x cubed minus 27,000. Now we could add 27,000 to both sides. 27,000 is equal to 8x cubed. 27,000 divided by 8, 3375. And if we cube root that, we get exactly 15. But again, there's no guarantee that this gives us our absolute minimum cost. So again, we have to find the second derivative, c double prime of c double prime will be 8. Then this will be plus 54,000. 54 with 3 zeros. Over x cubed. You can see then that c double prime, when I put in the 15, since there's nowhere to get a negative out of this, will have to be greater than 0. And therefore, you're going to be concave up, and you're talking about the point where the derivative was 0. So you're talking about this low point. Therefore, it's a relative min. And because there was only one, therefore, it's an absolute min. So you have an absolute min, it happens at x equals 15. So find the dimensions of the container of least cost. So we already know what one dimension is. X has to be 15, so the base has to be 15 by 15. And to get our other one, here we know that y has to equal 2250 divided by 15 squared is 225. And that is 10. So let us move on. A cone is made from a circular sheet of radius r by cutting out a sector and gluing the edges of the remaining piece together. What is the maximum volume? Right? So I chose this problem because you need to be comfortable working with variables, right? So I could have given you the problem with a fixed number for r, like with the radius of 10 inches, I could have said. But I chose to do this problem with a capital R here. And what you need to recognize is that that is a constant, right? So what is the maximum volume? So we want to maximize the volume. So we are going to cut out this little sector, glue it together as so we're going to cut out this little sector here, and we're going to glue it right there, right? And we're going to make this cone. So maximize the volume of a cone. Volume is 1/3 pi r squared h, where r is the radius of the cone, not the radius of the circle that you started with. This is a constant, right? So that's not changing. Okay, and so again, we have too many variables, so what we have to do is search for a constraint. And so your constraint comes from the fact that when you make your cone, if you come straight down and straight across, then this right here is going to be however big that was. And this right here is your height, and this right here is your radius. So now you see a right triangle right here, and so then the equation that relates these three things is that h squared plus r squared is equal to capital R squared. Okay? And so then, since we have an r squared here already, rather than solving for r, we can solve, rather than solving for h, we can solve for r squared. So then we can rewrite this formula as r squared is equal to big R squared minus h squared. And so then the volume is equal to 1/3 pi. The r squared can be replaced with r squared minus h squared, and then we have h. Okay, and so now your height is your input variable. And what kind of height can we use? Well, we can definitely use a height of 0. That will give us a volume of 0. Or we could use a height of r, and that will also give us a volume of 0. If we stand the cone up so that it goes up as high as the original radius. And again, the usefulness of this is both the endpoints give me an output of 0, so we know that we can't be looking at those. So it has to be some number in between 0 and r, right? And so if we distribute so that we can more easily differentiate, the volume will be 1/3 pi r squared so we're going to distribute the 1/3 pi and the h, and so then we will get r squared so we will get r squared times pi divided by 3 times h minus h cubed pi h cubed divided by 3. Right? So when we distribute this in, we'll have the r squared, the over 3h, r squared over 3h, but then we also have to distribute that, minus, we distribute the 1/3 pi, you'll get h squared over 3 times pi, but then you bring in the h, you get h cubed. Okay, so that looks right. Okay, so now we have to find the first derivative. And remember, all of this is a constant. So we just get r squared pi over 3. And then we bring down, we take the derivative of this, and the pi over 3 is a constant, so we just bring that down, and we get pi h squared. The only critical number on this, to find your critical numbers, set it equal to 0, and then you could add the pi h squared. is equal to r squared pi over 3. Multiply both sides by 3 over pi, and you will get h squared is equal to r squared, and so then h is equal to r. Ooh, something went wrong. If h is r, we get 0. So what did I do wrong? Okay, figured out what I did wrong. I added the pi squared to both sides, and somehow I magically ended up with a 3. So no 3 there. And so then all of this goes away. So we have r squared pi over 3 divided by pi, and so then h squared is equal to r squared over 3, and then when we square root, h will equal r over the square root of 3. And so then what is the maximum volume? This one is not asking us for the r, it's asking us for the maximum volume. And so then the volume, you can't plug this into your calculator. You figured out that your r value is r over the square root of 3. So you come over here to this formula and you substitute in your r over the square root of 3. So then it is so then it is well, let's just do that right here. R squared pi over 3 times r over the square root of 3 minus pi over 3 times h cubed, r over the square root of 3 cubed. And I'm sure we can clean that up, but I'm also sure I don't want to. So we're good. A man is floating in a rowboat 1 mile from a straight shoreline off a large lake. A town is located on the shoreline 1 mile from the point on the shoreline closest to the man, as suggested in figure exercise 58. He intends to row in a straight line to some point P on the shoreline and then walk the remaining distance to the town. To what point should he row in order to reach his destination in the least amount of time if he can walk 5 miles per hour and row 3 miles per hour? Okay, so a man is floating in a rowboat 1 mile from a straight shoreline. So there's the shoreline, right? A town is located on the shoreline 1 mile from the point on the shoreline closest to the man. So here's the man. And if he goes straight at a 90-degree angle there, that distance is 1 mile. Okay. A town is located on the shoreline 1 mile. And so then your town is over here, and it is also 1 mile from the point on the shoreline closest to the man. As suggested in figure exercise 58. I did not give you the figure because I expect you to be able to draw your own pictures, and so that's how we get that. He intends to row in a straight line to some point P. He's going to come here to some point P. and then walk the remaining distance to town. To what point should he row in order to reach his destination in the least time if he can walk 5 miles per hour and he can row 3 miles per hour? So the distance is least if he rows straight to the town, but he can row slower than he can walk. So then he doesn't want to go straight to the town, because then that would take him more. That's the least amount of distance. So instead, he's going to row to some point P, right, and then walk the remaining way, right? And so we want to keep track of where he rows to. So we'll call the distance from there to there x. And then you should take some time to write down, well, how far is it? What expression can I write for the distance from the point he rowed to here? And if you paused it and now resumed, then it should make sense that because that was 1 mile, this should be 1 minus x, right? And so then to what point should he row in order to reach it in the least time? So we want to minimize the time. And so then the time, the distance is equal to the rate. The distance is equal to the rate times the time. So the distance is equal to the rate times the time is the formula you should know. So the time is the distance divided by the rate. So then the distance that he is going to row is the distance from here to here. And we will call that y. And so then the time is going to be y divided by the rate. But then you have to add how far he has to walk, which is 1 minus x divided by by his rate there. He can walk 5. Right? But now we have too many variables, right? But we have a nice quadratic equation there where you can, you have a nice right triangle there where you can see that the x squared plus 1 has to equal the y squared. And so then y is equal to x squared plus 1 to the 1/2 power. And so then the time will then equal the x squared plus 1 to the 1/2 power divided by 3 plus the 1 minus x divided by 5. Okay. And again, x is how far off the original one he hit. So you can see then that x could be 0, you could go straight down, or x could be as big as 1. Now, again, your time is not going to be 0 at 0 or at 1, and so then you're going to have to plug those points in as well as the critical point. So for the critical point, we need to find the derivative. So we have a composition, bring down the exponent. make the denominator 6. Take 1 away from the exponent. Negative 1/2 times the derivative of the inside, 2x. Minus, this is just a constant, and the derivative of this is 1. So we get 1. Set it equal to 0, so we'll put this 1 over here, and then we will have 2x over 6 times the square root of x squared plus 1. Multiply both sides by the 6 times the square root of x squared plus 1, and we will get 6 times the square root of x squared plus 1 needs to equal 2x. Square both sides, and you get 36 times x squared plus 1 is equal to 4x squared. Distribute, and you get 36x squared plus 36 equals 4x squared. I just caught a mistake. The derivative of x is 1, but this minus is minus 1, but you still have this 5. So this should be minus 1/5. Okay, and so that means then that we have to start over. And so then when you set the derivative equal to 0, you will have 1/5 is equal to 2x over 6 times the square root of x squared plus 1. And if you cross multiply, bring it over here. If you cross multiply, you will get 6 times the square root of x squared plus 1 will equal 10x. And now if you square both sides, you will get 36 x squared plus 1 is equal to 100x. And then if you distribute, you get 36x squared plus 36 is equal to 100x squared. Sorry, we squared both sides. So this should be x squared. And now we get 36 is equal to 64x squared. And if we square root both sides, we'll get 6. Let's just divide by 64. And so then you'll get 36 over 64 is equal to x squared. And so then x is equal to 6/8, which is 3/4. And so then you then have to make a table . Make a table and plug in your endpoints, 0, 1, and your 3/4. So x here represents how far to the right I went. T represents how much time it took me. If I landed here if I went straight to the shoreline, The calculator tells me that it would take me 0.133. Okay, so I noticed another problem. I noticed that I have this plus here. I'm sorry, that minus there should have been a plus. But then when I took my derivative, I got lucky and got the correct sign on that minus 1/5. So when I take the derivative of this is -1, and so then it should have been a plus 1/5, but I made two mistakes and they corrected themselves. So we're okay there. Except that then when I went to go and plug this into my calculator, I plugged in this incorrect formula right there. So then when I do this, this is 0.533, which makes sense. And then this is 0.4714. And then this is 0.4667. And so then he should point to this is your absolute min, and he should point to 3/4 away from the perpendicular distance to the shore. Okay. One more. So you have a commercial cattle ranch currently allows 20 steers per acre of grazing land. On the average, its steers weigh 2,000 pounds at market. And it says estimates by the Agriculture Department indicate that the average market weight per steer will be reduced by 50 pounds for each additional steer added per acre of grazing land. How many steers per acre should be allowed in order for the rancher to get the largest possible total market weight? So kind of tough to just see that and make a formula. So what we have here is a commercial cattle ranch currently allows 20 acres per steer, 20 steers per acre of grazing land. So steers per acre. So we'll make a table. Steers per acre. Weight per steer. And then total weight. Okay. So if you allow 20 steers per acre, and then each steer will weigh 2,000 pounds. And so then 2 times 2 is 4, and you will have 4 zeros, the total weight will be 40,000 pounds of steer that you will get per acre. Okay, so now estimates by the Agriculture Department indicate that the average market weight per steer will be reduced by 50 pounds for every additional steer per acre of grazing land, right? So if you increase this So if you increase the steers per acre to 21, now you're going to lose 50 pounds per steer, and you're going to get 1950. And so you might be wondering, why would you do that? But the reason why you would do that is because the 21 times the 1950 is going to give you a slightly bigger 40,950 total weight. Likewise, if you increase this to 22, now you're going to drop another 50 pounds, per steer. So now you're only at 1900, and then the 22 times the 1900 is 41,800, a little bit more, right? Now, you should take a moment. Again, pause. It's very difficult to have come up with this table on your own. But now that I've shown you the table, okay, what we want to maximize is the total weight, and we want to connect the total weight to the steers. See if you can't find a formula that'll connect the total weight to the steers per acre, right? Now, okay, so here's a hint. If you just look at the first two columns, you'll realize that as the input increases by 1, the output decreases by 50. So that means that it is linear. So linear means that y is equal to mx plus b. Okay, but your slope is negative 50, and you know that if your input is 20, your output is 2,000. So you have 2,000 is equal to, your slope is negative 50, because every time you increase by 1, you drop 50. And then you know that your x is 20 plus b. So negative 50 times 20 is negative 5 times 2 is 10, and then you throw in a couple of zeros, negative 1,000 plus b. So then you add that to your 2,000, and so then your b is 3,000. Completely nonsense. It says that if you have no steers, the average weight per steer is 3,000, but that's not important, right? And so then you get that your y, the weight per steer, is related to your x, how many steers, by this formula, negative 50 times x plus 3,000. So the negative 50 means you're going to drop 50 every time you add one steer. And you can see that if you put in the 2,000, you'll get the 3,000. Okay, so now we can put x here, and then we know that this will be negative 50 times x plus 3,000. And then what we were doing to get the total weight is multiplying these together. So the total weight is x times negative 50x plus 3,000. So then we have our formula that relates the total weight to our steers per acre. So that would be negative 50x squared plus 3,000x. We can find the critical points. Take the derivative, negative 100x plus 3,000. And then we can set it equal to 0. 100x is equal to 3,000. And so then x is equal to 30. We only have one critical point. So since we only have one critical point, if it's a relative max, it's an absolute max. Of course, we only have, of course it's a absolute max, because what you're looking at is a parabola that opens down, right? So, and this is how many you need. Okay, so we're done with that.